Thanks for the invitation, and it's a great pleasure to speak here. But it's pity that I could not come due to the travel restriction. So today I will talk about the parallel transport for Higgs bundles over p-adic curves. So let us first review some classical results over complex numbers. Suppose we have a smooth projective variety over a complex number. Then we have the Hodge decomposition. That is, the singular cohomology of X can be decomposed as a direct sum of the Hodge cohomology. And then there's a generalization, is so-called the non-abelian Hodge theory, which provides a generalization for cohomologies with coefficients. So a very first result in this direction is the Narisman-Seychelles correspondence. It treats the dimension 1 case. And in the curve case, it establishes a bijection between the irreducible unitary C representation of the topological fundamental group and the set of a stable vector bundle of degree 0 over X. And the construction is given by as follows. If we have a representation V, and then we associate, we consider the product of the universal cover X tilde of X and V, and then quotient out by the diagonal action of the topological fundamental group of X. And here let us briefly recall that a vector bundle is stable or semi-stable, means for any subvector bundle F of E, the slope of F is less or equals to that of E, and the slope is defined by degree quotient rank. And then one can extend such a bijection for all C representation. To do it, we need to introduce the notion of Higgs bundles. That is a pair of vector bundle E over X together with OX linear map theta called the Higgs field from E to E tensor omega 1, satisfying theta wedge theta equals to 0. And then the Simpson correspondence, Hitchin-Simpson correspondence establishes a bijection between irreducible C representations of pi 1 and the set of stable Higgs bundles with 0 Chern classes over X. And note that this bijection works in higher dimensional case. And it is, in the curve case, it is compatible with the Narisman-Seychelles correspondence introduced in last page. And to relate to correspondence, the left vertical map is given by the nature inclusion. The right vertical map is given by associate each vector bundle to Higgs bundles with 0 Higgs field. And here the stable and the semi-stable properties for Higgs bundles is defined in a similar way for vector bundles. Moreover, under this bijection, one can compare the cohomology of two sides. That is to say, if we have a representation V and the E theta is associated Higgs bundles, then the cohomology of V is isomorphic to the Higgs cohomology of E theta. Okay, let us turn to the Piatic theory. We first fix some notation. K is a finite extension of QP, and we fix algebraic closure K bar. And GK is the Galois group. And OK bar is the ring of integers. OC denotes the Piatic completion of OK bar, and the C is its fraction field. So suppose we have a smooth proper variety over K, and a famous result analog of Hodge decomposition in Piatic theory is the Hodge-Tate decomposition due to Faltings, Nizio, Tsuji, and then generalized to rigid analytic variety by Schultz. it says that there's a canonical GK equivariant C-linear isomorphism between the p-adic étale cohomology of X of the geometry fiber of X, base change to C, and it decomposes as a direct sum of the Hodge cohomology twisted by C minus J. Let me briefly explain the Galois action on both sides. On the left-hand side, there's a nature Galois action on étale cohomology. And on the right-hand side, the action on Hodge cohomology is trivial. And then C minus J means twist by powers of p-adic superatomic characters. Okay, and we will talk about some non-abelian theories in this in p-adic Hodge theory. But the very first result is the p-adic Simpson correspondence, initiated by Faltings and then developed by Abes-Gross and Tsuji, that has already explained in Abes lectures. And another one is the p-adic Riemann-Hilbert correspondence, which focuses on the drum aspect, developed by Liu and Zhu, and also by Diaolan, Liu, Zhu. It is also used in Petra's talk on Monday. Okay, today we will mainly talk about the first the first one, the p-adic Simpson correspondence. Let me briefly review a little bit the results. Okay, we first take OC flat to be the for Venus the perfection of OC quotient POC, and the A-inf the ring of vector of OC flat. And there's a famous Fontaine's theta maps surjectively to OC. And the kernel of this theta is a principal idea, and we take a generator C, and we set A-inf n to be the A-inf quotient C power n. In particular, OC is the A-inf 1. So we fix a smooth projective scheme over OK. Indeed, this theory also works with semi-stable reduction case, but we have to work with some log geometry. So for the simplicity of presentation, we just focus on the good reduction case. Moreover, as explained in Abes' lecture, we also need to choose some lift of the X base change to OC to A-inf 2. But in our lectures, we fix furthermore a family of smooth Cartesian lifts of Xn over of curly Xn over A-inf n. In the case n equals to 1, it is nothing but the OC X base change to OC. And here Cartesian means for the Xn plus 1s, the base change of Xn plus 1s to A-inf n is isomorphic to Xn. So such a, we will see that why we need such a liftings later. So roughly speaking, such a smooth Cartesian lifting, curly X induce an equivalence between all the small generalized representations over X and the small Higgs bundles over X base change to C. And this is the p-adic Simpson correspondence. And I will explain these objects in more details in next page. And such a correspondence is established by a paired ring, C dagger, that explained in Abes' lecture. And okay, in the curve case, this functor can be furthermore extended to all generalized representation. And the category of generalized representation contain the category of the category of continuous finite dimensional C representation of the geometric fundamental group of X as a full subcategory. So in this talk, we will focus on this full subcategory of the C representation, and we will characterize the Higgs bundle associated with these C representations over curves. Okay, let me briefly review the objects. Two objects appear at the two sides of the Piatic-Simpson correspondence. The first one is the category of Higgs bundles that are denoted by HB, XC. This is the pair. It consists of pair M theta, where M is a vector bundle, and the theta is an OX linear map from M to C inverse M tensor with omega 1 XC, and together with this together with a theta wedge theta equals to 0 condition. And we say a Higgs bundle is small, which is a condition relative to our model X. It means there exists a model of a vector bundle as a coherent module on X base change to OC, such that the Higgs field sent this model M circ to p power alpha times M circ tensor with omega 1. Here, alpha is a rational number bigger than 1 over p minus 1. Okay, and on the other hand, we also consider the category of generalized representations. Roughly speaking, there are some modules in Faltings topos in the Faltings ring topos defined by X. And as explained in Abel's lecture, locally generalized representation are just representation of pi1, a geometric fundamental group, over some finite projective modules over certain p-adic ring. And we will discuss this object later. An important feature is that the category of finite dimensional C representation is contained in the category of generalized representation as a full subcategory. And we say a generalized representation is small if locally as a representation of pi1 admits a basis whose pi1 action is trivial modulo p power beta for some rational beta bigger than 2 over p minus 1. So we can see that the smallness condition means that the object that we consider are close to the trivial object modulo some power of p. And it's an important result due to Tsuji that the small generalized representations that we discussed here is same as the double modules. Here, double modules are those generalized representations satisfying the admissible condition defined by C. Dagger that introduced in Abel's lecture. Okay. So let me write down pictures for the objects that we consider so far. So in the top, we have an equivalence between the small generalized representation and the small Higgs bundles. And in the curve case, we can extend such a functor for all generalized representation to the category of Higgs bundles. And the moreover, the category of C representation is contained in generalized representation. And in this way, we obtain a functor. both H from this category to Higgs bundles. And indeed, these extensions that are denoted by H curly X exponential is defined by a choice of exponential map. So let me briefly explain what is this exponential map. So we know that we have the p-adic logarithm map from 1 plus the maximum idea of C to C. This is defined by the same formula for log as in real analysis. And on the other hand, the exponential map can only be defined on an open ball of radius less than p power minus 1 over p minus 1. And the exponential map is defined as the x tends to the sum of x power n over n factorial. And due to the p-adic convergences, it is only defined on a small open ball. And it is an inverse of log, p-adic log on this small ball B. But as 1 plus MC is a divisible abelian group, so our exponential map can be extended to a section of log from C to 1 plus MC. And it is a homomorphism with respect to the additive structure on C and the multiplicative structure on right-hand side. So this extension, H curly X exponential, depends on such a choice. And then, okay, let us focus on the one-dimensional case. And then we want to understand the essential image of this both curly X exponential. And it is expected that the essential image of this C representation in the category of Higgs bundles are those semi-stable Higgs bundles of degree 0 over X lower C. Indeed, Faltings sketch a proof of the inclusion from left-hand side to right-hand side. So today we'll describe, in this talk, we'll describe the essential image of this H curly X exponential with the help of functor due to the Niger-Wellner. This functor denoted by VDW. It is defined on certain vector bundles on the curve to the category of C representation of pi1. And then this functor also fits into above diagram. So one can view this functor as a p-adic analog of Narisman-Seychelles correspondence. So as I explained, so the compatibility of this functor with p-adic Simpson correspondence is also given by associate each vector bundle E to a Higgs bundle with trivial Higgs field. Okay. Let me briefly review the vector bundles introduced by the Niger-Wellner and how to associate C representation to these vector bundles. So we first recall that if we work in characteristic P, so let K be the residue of the p-adic field K, which is characteristic P, and we consider a smooth proper curve over the algebraic closure of K. And then a vector bundle E on this curve Z is called strongly semi-stable if the pullback of E by any power of the Frobenius map is semi-stable. And indeed, there are many examples of vector bundle which are semi-stable but not strongly semi-stable. The simplest example is that if the genus of Z is larger than 2, and then the push forward of the OZ by the Frobenius map is a stable bundle of rank P, but its pullback is not semi-stable anymore. And this is a definition of in characters P, and then Dunninger and Werner extend it to mixed characteristics as follows. Suppose we have a projective OK curve with semi-stable reduction, and then a vector bundle F on the base change of X over OC is Dunninger-Werner if for every irreducible component Zi of the special fiber of the curve, and we consider its normalization Zi tilde. The pullback of our vector bundle to the restriction, the pullback of our vector bundles to this normalization Zi tilde is strongly semi-stable of degree 0. And then we call such a vector bundle is Dunninger-Werner. That is to say, it emits a strongly semi-stable of degree 0 reduction. And then we pass this definition to the generic fiber by requiring that we consider its image of Dunninger-Werner vector bundles coming from the models. And then Dunninger and Werner provides another description for these vector bundles as follows. It shows us a vector bundle is dW is equivalent to the following properties. The second property is that for any positive integer n, after taking a finite extension of k, we can find a projective OK curve y with semi-stable reduction, and a proper map from y to x satisfying the following result, following properties. The first one is that the genetic fiber of F is a Galois étale cover. And moreover, we may assume that the Galois action extends to an action over the model y over x. And moreover, if we consider the pullback of vector bundle along this map F, we require it is to be trivial, to be a trivial bundle, modulo p power n. Indeed, this description of Dunninger-Werner's vector bundles allows us to associate the representations. Indeed, as Y has semi-stable reduction, there's a universal isomorphism between the push forward of OY and the OK. And if R denotes the rank of F, and then we have an isomorphism between the modulo p power n of the pullback of F by morphism F. The global section of this pullback and the modulo p power n, and a free module of rank R over OK bar modulo p power n of OK bar. But on the other hand, we know that this pullback, since this pullback is trivial, and the Galois action of Y over X also acts on the model. So we obtain an action, we obtain a Galois action on this global section. And then in this way, we obtain a modulo p power n truncated functor from the category of Dunninger-Werner's vector bundles to the category of representation of pi1. over the truncated ring OK bar modulo p power n. And then we take projective limits and inverse p. We obtain the deserved functor v dw. Okay, and indeed, in my thesis, we show that the Nigel-Wellness vector, the Nigel-Wellness functor is compatible with the p-adic Simpson correspondence. And recently, the Nigel and Werner extend their construction to higher dimensional case, and Wooten also compare their construction with the p-adic Simpson correspondence in higher dimensional case. Okay, this is some review of the Nigel-Wellness theory. So, any questions so far? Okay, next let us see how to extend their constructions to the. So, as I explained, the Nigel-Wellness series fits into a p-adic Simpson correspondence with 0 Higgs field. So let us see how to extend their theory to the Higgs bundles with non-trivial Higgs fields. So for simplicity, we just consider X as a smooth projective curve over OK. And then we consider the category, we introduce the category of Higgs bundles that denoted by HB dW over X base change to OC. This is the category of Higgs bundles whose underlying bundle M belongs to the category of the Nigel-Wellness vector bundle. That is to say, it admits strongly semi-stable degree 0 reduction in the special fiber, and equipped with a small Higgs field on M. That is to say, the Higgs field send M. The Higgs field theta send M to the p power alpha times M tensor with omega 1. And then we naturally extend this definition to the generic fiber, and denoted the associate category by HB dWXC. Okay, so so far we only treat the Higgs bundles. We only treat vector bundles together with a small Higgs field. But to extend the above definition for general Higgs bundles, we need a notion of the twisted pullback functor for Higgs bundle. This functor is compatible with the pullback functor reality of p-adic Simpson correspondence. Let me briefly explain the setup of this functor, and if time permits, I will talk about more details about this functor later. So let Y be a smooth projective OK curve, and then we take a smooth Cartesian lifting curly Y to A inf as before, and this lifting is about the in the case n equals 1. The curly y1 is just the base change of y to OC. And then we consider a proper map from y to x such that the generic fiber of F is finite. And this map F together with the lifting curly x and curly y, and also the exponential that we choose before. So this data, this 4 data induce a functor from the category of Higgs bundles over X lower C to Higgs bundles Y lower C. And why do we call it twisted pullback functor? Because for example, when Higgs field is trivial, this pullback is nothing but the pullback of vector bundle with trivial Higgs field. But when Higgs field is non-trivial, this pullback is different to the usual one by a twist. So I will. So if time permits, I will explain this twist later. And then, okay, with the help of the twisted pullback functor, we can extend the above definition in a more general context. And then we define a category of Higgs bundle that are denoted by HB PDW, lower curly x exponential. So, sometimes we just omit this lower curly x exponential, but the definition depends on this object. And the PDW stands for potentially Dunning-Werner. So this is the category of Higgs bundles m theta, such that we can find such a cover f from y to the x as above, such that the twisted pullback of these Higgs bundles belongs to the Dunning-Werner Higgs bundles over y lower c. So, okay, this is the definition. This is the Higgs bundles that we will consider. Okay, now I can state our main result. Indeed, the first one is that the Piatic Simpson correspondence h curly x exponential sends the category of finite dimensional C representation of the geometry fundamental group to the category of potentially Dunning-Werner Higgs bundles over x lower c that I just introduced in previous page. And moreover, we can construct a quasi-inverse of h lower x exponential that are denoted by v lower curly x exponential, and simply denoted by v if there's no confusion from the category of this potentially Dunning-Werner Higgs bundles over x lower c to the category of finite dimensional C representation of the geometric pi1. And moreover, as in complex case, moreover, if we have Higgs bundles and V is the associate representation, we can compare the p-adic étale cohomology and Higgs cohomology of E theta. Okay, this is our main result. And we have some partial results on the description of the Higgs bundles that we just introduced. We show that, indeed inspired by Faltings argument, we show that this potentially Dunning-Werner Higgs bundles belongs to the category of semi-stable Higgs bundles of degree 0 over x lower c. And the second point is that every Higgs line bundles of degree 0 belongs to this category. And moreover, as we establish the equivalence, we can see that this category is abelian and also is closed under extensions. And as I mentioned before, it is expected that the inclusion in assertion 1 of the proposition is equivalence. And I'd like to also mention that for Higgs line,
sorry, there's a question.
Yeah. So just because you restricted yourself to, for some reason, to for simplicity to smooth proper model. So I want to ask about this theorem. What is the definition that you use? So in the definition of potentially Denninger-Werner, you said that where is it? A smooth projective OK curve. So this includes the restriction it is smooth, and also that you don't change K to a finite extension. And it seems to me that this seems to be too restrictive, that maybe you need to allow extensions of K and semi-stable or other things.
Sorry. I'm tricking too much here. I want to say, indeed, in this definition, we require, after taking finite extension of K, and we take Y to be a projective OK with semi-stable reduction. So so here I need to replace this smooth projective by a semi-stable reduction, and moreover this cover usually appears after taking a finite extension of K, and then we define this potentially Denninger-Werner by pullback along this map F. Is this clear?
Yeah, please go ahead.
Okay. I want to mention that Ben Howard also treats the Higgs line bundles case of the Piatic-Simpson correspondence in rigid analytic varieties, and Howard, Mann, and Werner also treat the correspondence in the arboroid case. Okay. In the following,
a question.
Yeah.
Thanks. I was just wondering, do you know if systems of Hodge bundles lie in this category? So Higgs bundles which admit a decomposition such that the Higgs field shifts the decomposition, the ones which correspond to variations of Hodge structures classically.
Yes, this is a very interesting question. This, the Hodge bundle, it is expected that there are some Hodge bundles appear in this correspondence, and we want some good description of this. We expect some good description of the representation associated with these Hodge bundles, but I don't know too much results so far. But for example, if you consider some arithmetic local system and apply the p-adic Riemann-Hilbert correspondence, you can get some bundles with connection, with some bundle with connection, the Greenfield transversality, and then if you take graded, you might get some Hodge bundles. Yeah, this is some construction that I know.
Yeah. Okay, please go ahead.
Yeah. Okay. And okay. In the remaining of times, I will explain how to construct this functor V. So indeed, V is an extension of the Denninger-Werner's functor to Higgs bundles, and it is based on the Tsuji's approach to Piatic-Simpson correspondence. And so in the following, I will explain his approach to Piatic-Simpson correspondence. And indeed, in this approach, small Higgs bundles are interpreted as certain crystals on a site that are denoted by curly X or A-inf. Here curly X is the p-adic completion of X base change to OC. Indeed, in Tsuji's theory, there's many variants of these sites, and in the following, in the following, I will present a simple one, and also the one without the log structure. So, and an object of this site consists of two objects. The first one is a sequence of morphism curly T from T1 to T2 and to Tn to Tn plus 1. This each Tn is a p-adic formal scheme over the over the formal spectrum of A-inf quotient curly C power n, and this formal scheme is also considered as p-adic formal scheme. And we require curly T satisfying the following condition. The first one is that each Tn to Tn plus 1 is a closed immersion. And for n bigger than 2, we require that the reduction modulo P of the curly Tn to Tn plus 1 is a nilpotent immersion. And moreover, we require that Tn is p-torsion free for all n. And then we require that the kernel of O curly T big N to OT small n is defined by a principal idea generated by C power small n. And moreover, we require that the multiplication by C on OTN is C power n minus 1. So this is quite some technical condition, and the second part of the object Z is a morphism from the special fiber T1 to curly X. Sorry, to frac X. And a map of p-adic formal scheme. And so a morphism of two objects is defined in a natural way. It is a family of compatible morphism Fn over A-inf quotient Cn, such that they are compatible with the first truncated part is compatible with Z and Z prime. Okay, so on this side is a crystalline-like site, and we will equip with a topology defined by coverings as follows. So a family of morphism U alpha is a covering if each U alpha n is étale, and it is Cartesian, which means U alpha n plus 1 reduction to the modulo C power n is isomorphic to U alpha n. And moreover, I will require that the truncated one part is really a covering on the underlying set. Okay, and then we can also consider structure shift on this site. It is defined by a functor associated to curly T Z to the global section of the truncated one part of T, and this defines a shift of rings that are denoted by O bar frac X over A-inf. And we will also consider the reduction modulo P power n of this O bar, and also the inverse P of O bar. And then we can also define the notion of crystal of O bar inverse P modules on this site. It is defined in a similar way as in crystalline sites that I denote this category by HCQ, frac X over A-inf. Recall that in p-adic Simpson correspondence, we choose a smooth Cartesian in this case, we choose a smooth Cartesian formal lift, curly X of frac X over A-inf. And this really defines the object of the size that we consider. And then once we choose such a lifting curly X, and then the evaluation at curly X induce a functor from this crystal to the category of Higgs O frac X inverse P modules with suitable conversion condition on Higgs field. And then indeed, Xu show that the category of small Higgs bundles is contained on in the essential image of iota curly X, and we denote it by HCQ phi, its essential image. Here phi means some finiteness and projectiveness properties on the crystals. Okay, indeed, one can indeed in Xu approach, you realize the Simpson correspondence directly from Higgs crystals to generalized representations. Let me briefly explain these constructions. Suppose we first consider a local case. Yeah, we will only consider a local case. That is to say, X is the spectrum of R, and admits a étale map to GM to some power of the torus. Let Vi to the geometric generic fiber of X be the universal cover of X space change to Xk bar, and then let Ri be the integral closure of R in Vi, and consider R bar the direct limits of all this Ri. Then the geometric fundamental group denoted by delta acts continuously on the p-adic completion of R bar that are denoted by R bar hat. And the generalized representation in the local case, just representation of delta on R bar hat inverse P modules. And semi-linear representations of delta on R bar hat inverse P modules. And if we have a small Higgs bundles and consider the associated crystal curly M. Okay, and then we consider the A-inf of R bar and truncated by C power N. And this family also defines, in local case, also defines an object of the site that we denoted by D. And the delta naturally acts on this object D, and then induce a functor from the category of crystal by evaluation of the crystal at this object D. And then we obtain a semi-linear representation. And such a construction can be globalized from the category of crystal to the category of generalized representation, and is independent of the choice of curly X. And once we choose a curly X, smooth Cartesian lifting curly X, and then we can use the equivalence between small Higgs bundles and these crystals, and these Higgs crystals to define a functor from Higgs bundles to generalized representation. And this functor, the image of this functor is contained in small generalized representation, and is a quasi-inverse of the Piatic Simpson correspondence H curly X that I present in the beginning. And moreover, the advantage of this construction is that it also applies to certain, so I mean the functor V also applies to certain integral or torsion Higgs bundles or crystals. And finally, I want to remark that one can mimic this argument to applies to crystals on prismatic site. For example, in Xu's talk, he mentioned he explained his joint work with Morrow, and there's also a recent work of Yu Min and Yupeng Wang. They treat some Hodge-Tate crystals on prismatic side. Okay, and then I want to mention that the advantage of another advantage of this site theoretic point of view is that we have a nature pullback functor reality. Indeed, a morphism, suppose we have a morphism of smooth projective curve or projective curve with semi-stable reduction, such that the generic fiber is finite étale. And then we have it naturally induced morphism of tuples. And then if we consider the pullback functor, it sent Higgs crystals over frac X to Higgs crystals over frac Y. And then this pullback functor, it's easy to see that this pullback functor is compatible with the Piatic Simpson correspondence, Vx and Vy, and the pullback functor reality for generalized representation, because Vx and Vy are defined by evaluation. And in particular, if you translate this pullback functor in the language of Higgs bundles, it is compatible with the twisted pullback functor F circle after choosing some smooth Cartesian liftings, curly Y and curly X, and via the equivalence between Higgs bundles and Higgs crystals. Okay, yeah, maybe I don't have time, so I just skip this part about the construction of this twisted pullback functor for Higgs bundles. So in the end, I want to mention that how do we use the notion of Higgs crystals to extend the trivializable property for Dunninger-Wellness vector bundles to Dunninger-Wellness Higgs bundles. Indeed, here's our main result. Let M be a vector bundle of rank R over X space change to OC, and theta a small Higgs field on M, and consider curly M the associated Higgs crystal. Then the following condition are equivalence. The first one is that the M theta belongs to HB dW, that is to say the vector bundle M has a strongly semi-stable reduction. And then another description is that for every integer, positive integer n, after taking a finite extension of k, then we can find the projective OK curve y with semi-stable reduction, and a proper map from y to the x, such that the generic fiber of fk is finite étale. And moreover, if we consider the pullback of the this Higgs crystal curly M modulo curly M, and consider its reduction modulo p power m, then it is trivialized on the category of Higgs crystal, on the category of p power n torsion Higgs crystals on frac Y or A inf. This is the generalization of the Dunninger-Wellness result, Dunninger-Wellness trivializable result to Higgs bundles in terms of language of Higgs crystals. Okay, and then to construct this functor, and we will use this trivializable property to construct functor V, and we may assume moreover that the geometry generic fiber of F is a Galois étale cover, and the action of the Galois group extends to the model Y to the X. And the idea of the proof of this theorem is that we can find the covers, such a covers, trivializing bundles, and also or trivializing the Higgs field modulo some power of p. To trivialize Higgs field, it's sufficient to find a cover f to y to the x, such that the pullback of f on the h1 of O, h1 of coherent cohomology of O is become p power divisible after suitable pullback. Okay, and then we combine these covers together, and then we can prove this theorem. Okay, finally, let me explain how to construct functor V. And we take such a Higgs bundle m theta of rank R, and then we consider the associated Higgs crystals, and consider n a positive integer n, and then we choose a proper map of curves, trivialize our Higgs crystal m modulo p power n as above, and then we know that the as mn is trivialized after pullback by the pullback functoriality of Piatic Simpson correspondence, the generalized representation Vxmn also satisfy a similar trivializable properties in Faltings topos of Y. That is to say, if we consider capital phi, the functorial map of the Faltings topos, the pullback of Vxmn by phi is also trivial. And then the Faltings comparison theorem tells us that the global section of this trivial, the global section of the structure shift B bar Y modulo p power n in the Faltings topos E tilde Y is almost isomorphism to OC quotient p power n. So in this way, we obtain this isomorphism between the global section of the, this is phi. Between the global section of Vxmn, this and the pullback by phi, and the free OC quotient P and OC modules. And on the other hand, as in the Daxin Xu theory, there's a nature of Galois actions on the left-hand side. So in this way, we obtain our functor Vn from the Daxin Higgs bundles to p power n truncated representation. And then taking projective limits, and then do some descent along this twisted pullback of Higgs bundles, we can extend our functor to all potentially the Daxin Higgs bundles on X over C, the base change to C. Okay, finally, let me remark how we also need to show that V is a quasi-inverse of H. That is, our functor V is compatible with Piatic Simpson correspondence. That is to say, we need to show that the generalized representations obtained by V associated to V is same as the generalized representations produced by Higgs bundles. So if you keep above notation, and such a almost isomorphism exists after pullback along our cover Y to the X, and is equipped with descent data. And then finally, we conclude this such an isomorphism by cohomology descent in the Faltings topos. And this is a result due to Tongmu He. Okay. Okay, this is end of my talk. Thanks.